Okay, so now we can talk about the definition of a derivative. We've been talking about different types of limits and everything that we needed to set up before we could officially talk about the derivative. The derivative is where we're going to spend most of our time and is probably one of the most important topics inside of calculus, business calculus. It's got very good applications to businesses and everything. So lots of people use derivatives inside there. So uh, if you don't learn anything else this semester, this is one of the most important things you need to learn is derivatives. Um, we'll soon see a different way of doing derivatives, which is a lot more streamlined, straight to the point than this. But this is kind of our intro section to it. So the first thing we talk about is the tangent line to the curve at a point. So basically what we're talking about is if we have any curve here that I can find a point and I can draw a line that touches our curve in only one spot. If I can find this line right here or this line right here, both of these are the tangent lines. In other words, by definition, a tangent line only touches our curve at exactly one spot. Now, the question is, how do we find some characteristics about this tangent line? Well, we look at our definition. So the slope of the tangent line to f of x at the point at a comma f of a is given by the limit as h goes to 0 of f of a plus h minus f of a all over h. Some notes about this definition here. The limit has to exist. So everything we've been talking about with limits must hold. Otherwise, there is no tangent at that point. If your limit doesn't exist, you can't have a tangent line there. Number two, the slope of our tangent line at x equals a is equivalent to the instantaneous rate of change at x equals a. So that same process we've just been doing with instantaneous rates, we're going to use the exact same process. You know, we may change these a's to x's in just a minute, but you know what? It's the exact same thing. So for example, it says find the slope of the tangent line of f of x at x equals 1 and the equation of the tangent line at x equals 1. So the first thing we want to do is we want to find the limit as h goes to 0, f of a plus h, so that's a plus h all squared plus 2 minus f of a, which is an a squared minus 2 all over h. So by simplifying this out, limit as h goes to 0 of a squared plus 2ah plus h squared plus 2 minus a squared minus 2 all over h. So at this point, we have the limit as h goes to 0. We can cancel out everything, cancel out. So we got a squared minus 2 plus 2. So we have 2ah plus h squared all over h. At this point, we have the limit as h goes to 0. Everything over there can be divisible by h. So we have 2a plus h. The last thing is to perform the limit, and we're going to let h equal 0 at this point to give us 2a. Now, we're not through with the problem now. All we did was find basically the instantaneous rate of change for any value of a. So now it says find the slope of the tangent line of f of x at x equals 1. In other words, let's let a equal 1. So 2 times 1 gives us 2. This is our slope. Now, the other thing that it told us to find over here was the equation of our tangent line. So in order to find a line equation, we need 2 points, or a point and a slope. So we have x equals 1. So let's find f of 1. So we get 1 squared plus 2 is equal to 3. So we have the point 1 comma 3 with a slope of 2. So y minus 3 equals 2 times x minus 1. So y equals 2x minus 2 plus 3. So y equals 2x plus 1 is the tangent line equation. So we found the slope of 2 by using our limiting process. We found the equation by having a point and a slope and plugging in. Now that was just to find our slope and everything. Well, if we change those a's to x's, we can actually define the definition of a derivative. So the derivative of function f at x is defined as f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So here is some new notation that we need to think about. This f prime of x. F prime of x is called the derivative of f with respect to x. If f prime of x exists, so that means our limit exists, then we know that f is differentiable at x. F prime of x is also a function of x. So whether or not you get f prime of x equals 2x, f prime of x equals x squared plus 3x plus 1, f prime of x equals 5, f prime of x equals 0. All of these are functions of x. F prime of a is equal to the slope of our tangent line at x equals a, which is equal to the instantaneous rate of change at x equals a. So we're still talking about this in terms of rates, that it's still a rate. dy dx is a rate, it's a slope. They're all rates right there. So we're told for f of x equals 2x squared plus 1, find f prime of x, then find f prime of 5. Okay? F prime of x is equal to the limit as h goes to 0 of f of x plus h. So 2 times x plus h all squared plus 1 minus f of x. So minus 2x squared minus 1 all over h. So this is the limit as h goes to 0 of 2 times x squared plus 2xh plus h squared plus 1 minus 2x squared minus 1 all over h. If we simplify this a little bit, limit as h goes to 0, we get 2x squared plus 4xh plus 2h squared plus 1 minus 2x squared minus 1 all over h. By looking at this now, we can cancel things out. So this is equal to the limit as h goes to 0, 2x squared minus 2x squared minus 1 plus 1. So we're left with 4xh plus 2h squared all over h, which is the limit as h goes to, notice that we have everything is divisible by h, so we have 4x plus 2h. At this point, let h equal 0. That gives us 4x. So this is our derivative f prime of x. The next thing it tells us to find is f prime of 5. So f prime of 5 is equal to 4 times 5, which is equal to 20 as our f prime of 5 value. So notice it's all the same exact stuff we've been doing, just now we're thinking about it with a different variable, a different name, but it's no different than what we've already been seeing. So we're told, find f prime of x when x is equal to 9 and x is equal to 81. So the first thing we're going to do is we're going to find f prime of x. So f prime of x is equal to the limit as h goes to 0 of the square root of x plus h minus the square root of x all over h, which is equal to the limit as h goes to 0. So what we have to do here is we need to think about this in terms of rationalizing. We're going to rationalize that numerator. So to rationalize the numerator, so we have square root of x plus h minus square root of x all over h. I'm going to multiply top and bottom by square root of x plus h plus square root of x in both cases, top and bottom. In the denominator, I am not going to multiply it out, so it's going to be h times square root of x plus h plus square root of x. In the numerator, we have a difference of squares, which is a minus b times a plus b, which will give us a squared minus b squared. And when you square a square root, the square root disappears, so we're left with x plus h minus x. So this gives us the limit as h goes to 0 of h divided by h times square root of x plus h plus square root of x. Canceling out our h's now. We have the limit as h goes to 0 of 1 divided by square root of x plus h plus square root of x. At this step, we can let h equal 0, which gives us 1 over square root of x plus square root of x, which is 1 over 2 root x. And this is equal to our f prime of x. It then told us to find f prime of 9 and 81. So f prime of 9, f prime of 81. So we get 1 over 2 times the square root of 9, which is 1/6. Because the square root of 9 is 3, 3 times 2 is 6. Then we have 1 over 2 times the square root of 81, which is 1 over 18, because the square root of 81 is 9 times 2 is 18. Now, we've been talking about derivatives without having to really dig deep into them. Meaning, we've assumed that all of our derivatives exist. What if it doesn't exist? So those are the that's the type of question we have to ask ourselves is, when does it not exist? So f prime of x does not exist at x equals a. This is going to be true a lot of times when we start talking about fractions, which is what we're fixing to see in a second. So it does not exist at x equals a if f of x is not defined at x equals a. So always, anytime you start, look to see where is your function not defined before you actually go into working it. Because if you can kind of think about what's your domain, where is it not exist, that kind of gives you some starting points and everything. The second thing, it does not exist at x equals a. The limit as h goes to 0 of f of a plus h minus f of a all over h doesn't exist, which means there is no tangent line at x equals a, which means at sharp points, corners, jumps, discontinuities, vertical asymptotes is our next place. So the vertical tangent line at x equals a means normally any rational function that has x in the denominator, it's going to have a tangent line somewhere, a vertical tangent line somewhere, which is where it does not exist. So that brings us to this problem. It says f of x equals -3 divided by x plus 1. Where does f prime of x not exist? And then what is f prime of 3? So f prime of x does not exist at x plus 1 where it equals 0. So in other words, we set our denominator equal to 0. So x equals -1. It does not exist at x equals -1. So that's the answer to our first one there. Now the next one's a little bit harder because we actually have to find the derivative before we can plug in. So f prime of x is equal to the limit as h goes to 0 of -3 divided by x plus h plus 1 plus 3 over x plus 1 all divided by h. So this is the limit as h goes to 0. We need to get a common denominator, so I'm going to cross multiply. -3 times x plus 1 plus 3 times x plus h plus 1 all over x plus h plus 1 times x plus 1. Since it's a division, we can take this h and just throw it in that denominator, and it's going to be fine. So simplifying this, we get the limit as h goes to 0 of minus 3x minus 3 plus 3x plus 3h plus 3 all over x plus h plus 1 times x plus 1 times h. Simplifying this, the limit as h goes to 0. So our minus 3x plus 3x plus 3h, plus 3 minus 3 cancels. Got a little ahead of myself. 3h is what we're left with up top, and then we have x plus h plus 1 times x plus 1 times h. So this is equal to the limit as h goes to 0. Our h's can cancel out now, so we're left with 3 over x plus h plus 1 times x plus 1. Here we can let h equal 0 at this point. So that gives us 3 over x plus 1 times x plus 1, or 3 over x plus 1 all squared. This is our f prime of x. Now way back up here, we wanted to find f prime of 3. So f prime of 3 is equal to 3 over 3 plus 1 squared, which is 3 over 16 as our answer here. So it's not a bad thing on what we're doing here in terms of lots of difficulty. It is long, lots of possibility for mistakes, but we can work through all that with practice.